Let's talk about color gates first. So this when we talk about addition, you know why. This gate, if this is A and B, and this is we'll call the output O. This is known as an, or sometimes you see a plus sign inside that. That's called an OR gate. So the output of that will be A, or plus means OR, B. So you'll see sometimes a plus inside that to let you know that's an OR gate. Me personally, I never put the plus there. Now the truth table for that, if these are your inputs, if both inputs are 0, the result is 0. 0, 1, the result is 1. 1 and 0, the result is 1. And 1 and 1, the result is 1. Basically, remember when we had this sign, we said that's equal to what? Less than or equal. So as long as you satisfy one of the condition, that statement is true. So if I said to you, is 5 less than or equal to 5? It satisfies the equal, it doesn't satisfy this, but that's still a true statement. So 1 here really means true, and 0 means false. So for this to be false, that means this has to be false, and that one has to be false. Once one of them is true, the result of this is what? True, and that's what this one is telling you. Once one of the output is 1, which means true, the result of that is 1. The only way to get a false statement, both have to be false at the same time. Both have to be 0 at the same time. Now, instead of this being a curve like this, if a straight line, that's an AND gate. This is A and B. That's an AND gate. And the AND gate to be true, for something to be true, if I said, well, I'm recording, I gotta be, okay. I was about to say, to pass this class, I'll say it actually, it's a joke, I'm just saying it's a joke. To pass this class, you have to have an average above 93 and give me $500. Well, guess what? You have to do both conditions to get A in the course. Even if you have 100 average, you will not get A in the course because it's an AND operation. So for AND to be true, that means you have to satisfy both conditions. If I said to you, to get A in the course, you have to have an average of 93 or higher, or give me $500. If I said, or, you can pack your stuff now and give me $500 and I have to give you an A. Because that's an or, you only have to satisfy one of the condition. That's why once one of these is true, the result is true. For the AND operation, both have to be true for the answer to be yes. So 0 and 0, that's 0. 0, 1, that's 0. 1 and 0, that's 0. And 1 and 1, that's the only time you get a 1. Or and. So to get a yes or a true statement, both conditions have to be true. That's the only time. To get a true statement for an OR gate, as long as one of them is true, the output is true. Go ahead, Ricardo.
Does that O or 0 on the AND or on the OR gate?
This one?
Yeah, what is that?
That's like an out.
Output?
Yep.
Okay.
Which I'm calling A plus B now. Yeah. Yeah, maybe 0 or O wasn't the right choice there for a letter to use, because might think it's 0 here. But that's an output, yeah. So the output here, we write that A and B. So now when we start writing Boolean algebra, you'll see that in a minute, but let me add one more before I forget, and that's the NOT gate. The NOT, like if this is X, this is X naught. For binary, you only have two options, ones and zeros, right? So if it's not 0, then what is it? 1. If it's not 1, what is it? 0. So it's the complement. It flips it. If it's 0, we'll make it a 1. If it's 1, we change it to a 0. We have these gates in the lab. We have devices that will do that in the lab. You get to see them on Thursday. You get to play with them on Thursday. But now we're going to use this actually and change it to Boolean algebra. Here we go. So this is Boolean algebra now. So I'm going to be writing, for example, if you look at that gate here, the OR gate, if I write A plus 0, what's the answer? In math, what's the answer to that if it's just pure math? A. Well, guess what? In Boolean algebra, it's still A. Why? Because it depends on what A is. If A is 0, what is 0 or 0? Gives you 0. If A is 1, what's 1 or 0? Gives you a 1. So this is still true here for Boolean algebra. A and 0. That's an AND gate. Notice here's my AND gate. If one of the inputs is 0, what is the result of that AND gate? 0. It looks like normal math, doesn't it? What's A or 1? Normally in algebra that's A plus 1, right? Here the answer is 1. We're saying if you have an OR gate and if one of the input is 1, I don't care what the other one is, the result is going to be what? 1. So that's different than normal math. What's A and 1? That's a multiplication. Could be a 1 or could be a 0. It depends on what? On A. If A is 0, the result is what? 0. If A is 1, the result is 1. So this will be an A. We know the complement. What's A plus A complement? Try again. 1. That's an OR gate. So if A is 0, what's the complement? 1. What's 0 plus 1? What's 0 or 1? 1. If A is 1, what's the complement? What's 1 or 0? 1 or 0 is still 1. So anything OR it with its complement is going to be a 1. Anything ANDed with its complement, that's a 0. What's A plus A? Now in algebra, that's 2A. Not here. A. 0 or 0, that's a 0. When it's 1, 1 or 1, that's a 1. So whatever A is, the answer is going to be A. What's A and A? That's also A, not A squared. If A is 0, what's 0 and 0? 0 if A is 1, what's 1 and 1? 1. If you take A naught and not it, a double complement will do nothing. By the way, our book really, it's hard to write the not. So to do the bar over them, they write them like this. They use that for not. Prime, because it's easier to type that on our computer. Otherwise, to put a line over, it's not that easy. So that's what most books will use. So this one will be A naught, the whole thing knotted. So they write it like this. And that's A. But that's what it means. I write them like this, but that's when you type them, you can't really type them like that. It's not easy to do that. Now, A times B plus C. Remember, that's distributive property. That would be what? A times B plus A times C. Now we have A plus BC. You can simplify that as A plus B, and I'll prove that, times A plus C. And let me stop, prove why that's true. So let me prove this one. Let me take the right side. If I do the FOIL method, that's still true here. So that would be what? A and A plus A and C plus A and B plus B and C. What's A ANDed with A? A. Let's look at these three here. Can you factor anything out of them? If you factor in A, what's left? 1 plus C plus B. Now this is an OR gate. An OR gate with one input is 1. What's the result of that OR gate? 1. Doesn't matter what C and B. Once you have a 1 for an OR gate, once one of the input is 1, I don't care what the other one, the result is 1. So this gives me a 1 here, A and 1. And what's A and 1? We listed that, that's an A. So that's why this is really equal to that. The nice thing about this, people say, does it really make a difference if I write them like this or write them like this? Well, let's look at the design of that. If you were to design this one says you have an AND gate with B and C going to it. See it? The result of that is going to be what? You're going to OR it with what? With A. How many gates you see there? 2. If you're designing this, what do you see? An OR gate and an OR gate. A and B. I see another one, A and C, And the result now is what? And it together. How many gates I'm using there? 3 gates versus 2. Now this is a 2-input OR gate. Well, when you buy a chip, it has 4 of them. So if you need 1, 2, 3, or 4, it doesn't make a difference. The same chip. But when you're building a big circuit, you save an OR gate here, you save an OR gate here, you save an OR gate here, an OR gate there. There goes a chip off the board. So you're going to see us actually go through the Boolean algebra, try to take some ugly expression, a bigger one, simplify it so the design is smaller. That's what we're trying to do with the Boolean algebra. Simplify that expression. Another way to prove these are equal, if you don't have Boolean algebra, another way to prove are they really equal. I'll show you how another way of doing it is called using the truth table. Let's say I want to prove that A plus BC is equal to A plus B and with A plus C. I can do that. Graph paper will come in handy here. I have 3 inputs, A, B, and C. Let me list the combination. What's 2 to the power of 3?
8.
I'm going to have 8 combinations. So I'll start 0, 1, 0, 1, 0, 1, 0, 1. That's 8. 0, 0, 1, 1, 0, 0, 1, 1. The next one is what? 4 zeros and 4 ones. That's one easy way to write all the combinations. If you look at the binary value for the 0, 1, 2, 3, 4, 5, 6, and 7. Now let's see. I want to prove that A plus BC is equal to the one above it. So let me find out what A plus BC. That means I need to find first what BC is. So let's find BC. This is B and C. What's 0 and 0? That's an AND. What's 0 and 0? 0. What's 0 and 1? And. What's 1 and 0? 1 and 1. 0, 0. 0, 1. 1, 0. 1 and 1. 1. For an AND gate to be 1, both inputs have to be 1. Now let's add to that A plus BC. That's an OR. This column is A and this is BC. Can you see them? OR here, not AND, OR. What's 0 or 0? 0. What's 0 or 0? 0. 0 or 0? 0 or 1? 1 or 0? 1 or 0? 1 or 0? And 1 or 1? 1. That's A plus BC. Let me find the answer to this one and see if it's equal to this one. So I need one column that has A plus B. Maybe I should use a different color for that.
Are we testing the second one now?
Yep, I want to see if it gives me the same result. Maybe I'll use red for that. Or blue. Or blue. I want to see if it's equal to, so I'm doing here A plus B. I'm finding the answer to this. This is A and this is B. I'm doing the OR. 0 or 0. 0. 0 or 0. 0. 0 or 1. 1. 0 or 1. 1. 1 or 0. 1. 1 or 0. 1. 1 and 1. 1. 1 or 1. 1. Let me find A or C now. That's the first and the last. 0 or 0. 0. 0 or 1. 1. 0 or 0. 0. 0 or 1. 1. 1 or 0. 1. 1 or 1. 1. 1 or 0. 1. 1 or 1. 1. Now let me find A plus B and it multiplied by A plus C. That's this column with this column, and, not or. What is 0 and 0? 0. 0 and 1. 0. 1 and 0. 0 and the rest all 1 and 1, which is 1. Now compare this one to this one. Are they the same? No, it's the same output. So they are equal. So that's one way actually, if you don't know Boolean algebra, if we said, are these two equal? That's one way to test it. Yes?
How do you determine the initial A, B, and C? Do you just memorize them?
Well,
The order, I know it's a pattern.
yep. Well, notice it's actually 0, 1, 2, 3, 4, 5, 6, 7. That's why I'm listing all the combination that exists for them. So there are, since there are 3 variables, there are actually 2 to the third, which is 8 different combination.
Yeah.
If I had 4 variables, that's 2 to the 4, which is 16 combinations. So I can try to list them all and see which one, but the easiest way, go alternate every other one first, every 2, every 4, every 8, every 16, every 32. That'll give you all the possibility in nice order. It'll be like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth. Or you can go, this is the 0, this is the 1, this is the 2. Like if I had 4 variables.
Okay, yeah.
Make sense? Yes. Okay. Let's try another truth table.
Yeah, probably. Yeah, probably should. If you were to swap C and instead of swap A with switching every other one, would that still work out the same output?
If you swim, if you swap C.
Say if C is 0, 1, 0, 1, 0, 1, 0, 1.
You can do it, but then you have to think what the other one should be.
Okay.
Because you're trying to cover all possibilities. So I can actually go crazy with it. I can go A, B, C. I might go 0, 1, 1. I'm going to start with that. And 1, 0, 1. And 1, 1, 1. And 0, 0, 0. I'm not following any pattern.
Right.
So I have to list when you have 3 combinations. That's 2 to the third, which is what? 8. So I need to cover 0, 1, 2, 3, 4, 5, 6, 7. This one covers which one? That's the 3. 0, 1, 1, that's 3. 1 and 2 and 4. 1, 2, 4. 1 and 5 is what? 1 and 4 is what? 5. 1, 2, and 4. That's the 7. This is the 0. So I cover this. I cover this. I cover the 5. I cover the, I need the 1. I can put the 1 next. That's the 1. Let me do the 6. What's left? The 2. And the 4. So that covers all the possible. But it looks messy. It's all over.
Yeah.
It still will work. So if you want the easy way out, you just, oh, never mind this. I'll just go every other one. every 2, every 4. Notice that's 0, 1, 2, 3, 4, 5, 6, 7. It puts them in nice in order there. That's actually the nice thing about doing them this way. You can list all the combinations in a nice order.
Okay. And then if it was 4, 4 would be every
If it's 4, so it would be like, you're going to go 0, 1, 0, 1, 0, 1, 0, 1.
for the fourth column, though.
0, 0,
Right?
yep, 0, 0, 1, 1, 0, 0, 0, 0, every 4. Then you go every 8. And if you count them, that comes 0, 1, 2, 7, 8, 9, 10, 11, 12, 13, 14, 15. It puts them right in order. Now, let me write an expression here. A B naught plus B C naught D plus A naught D plus E. If I was to build this, if I was to go to the lab and build this, I have A, B, C, D, and E, right? I get 5 inputs. So to build this, to design it, first I'm going to need what? B naught. So I'm going to take the B, I'm going to go through and get a NOT gate, one of those chips that has a NOT gate, and put the NOT gate through it. Coming out of this NOT gate, what are you going to have? B naught. I'm going to take this and it with what? That says and here, with A. The next one, I need a bigger AND gate, 3 inputs. I have B, I got D, and I have C. I got to NOT the C. And that's the other AND gate. I have another AND gate with 2 inputs. And finally, you take all 3 of them, the result of each one of these with E, and what do you do with them? You OR them together. And that's my output. What I don't like about this, I know when I go to my drawer looking for the gates, I can get one chip that has 4 2 inputs AND gate. I'm going to write capital N. Oh, back here, brand new one, don't break it. You'll see we have to be very creative in the design. Has 4 of them on one chip. So I get to use this and this on it. This is a 3 input AND gate. I do have chips in the lab. They have 3 of them, not 2, not 4, but it has 3 input AND gate. So for this, I gotta grab another chip and use one of these 3 inputs. For the NOT, it's not a big deal. We have a chip that has 8 NOT gates on it. So I need 1, 2, and 3. It's not a problem. I had 8 of them on that chip. So I need one of those chips. I need one of those. I need one of those. Now I need 4 input. There is a chip, actually. We have a chip in the lab that has 4 inputs and an OR. We have ones for AND. We have one for OR. Somebody asked, can you really eliminate a chip? I said, sure we can. I need one of these, one of these, one of these, one of these. Here's the problem. This one has 4 of them. I'm only using 2. There's 2 empty ones. This one has 3. I'm only using 1. There's 2 empty ones. I'm wasting money left and right.
You should just use the 3 input AND gates instead.
I could actually. Good answer. I could take this one out and says use 3 input. Well, but this one has 2 input. What do you do with the third one?
Useless.
No, you're going to connect it somewhere.
Tie it to high, make 1.
If you tie it to high, you killed it because it becomes 1. So I could eliminate this. And I like, by the way, that choice. It says, hey, why use this and this? Why not take this one out? Since the chip has 3 inputs, this one I need 2 of them. So here's my chip. This is just the chip for the AND. 3 inputs AND gate. It has 3 of them on it. This is 1. So I can attach B here, take it through the NOT gate, that's the other chip, and bring it to this. And there's the A. I'm looking at the top one. But it has an extra input here. That you have to ground. Because if you make it, that's an AND. I thought it was an OR actually. An AND you have to make it a 1, not a ground. If you make it a 0, what will happen to that AND gate? It will always be 0. I thought it was an OR gate. I overslept there. That's an AND gate. So I want that to be a 1. Because when you put a 1, your output depends on these. If you put a 0, it doesn't matter what these are, your output is 0. So that takes care of that. I'll take the other one that you see there. And that's this one. And the third one, that's A, that's D, and the third input is what? 1. You attach them like this, you eliminate one of the chips. Gone.
How much more expensive are the 3 inputs than the 2s?
A little bit more expensive. So since the cost is a factor, okay, I'll take that option. The next question is, but the 3 input, gates, they might be more expensive than 2 input, probably, but not a lot because this has 4 of them. It might be a few pennies more, so I can fix that. How do we fix it? Instead of using this, how about use that one only? 4 2 input AND gates. That's what my chip will look like. 4 2 input AND gates. So you get 4 of them. The first one is a 2 input AND gates, not a big deal. And this is A. That took care of that one, right? This one, leave it alone. Let's look at the bottom. Yep. And let's see this one. I can take B here. I can take C. Take the result. and added with the D. And now I got my 3 input AND gate by doing this. So now I managed to eliminate the 3 input AND gate and use the 4 2 input AND gate chip. I do this all the time. I walk into the lab, I go, I need 3 input, I can't find one. What do I need to do now? I need a NOT gate. I don't have a NOT gate. What do I do? How do we fix that? So that's what we're going to be doing in this class. How can I eliminate some of these chips? That's where Boolean algebra comes in, if I can simplify the expression or not. This, mathematically, I might not be able to simplify it, but at least in my design, instead of using a chip, a chip, a chip, and a chip, 4 of them, I can eliminate this or that, see what the price is, which one's cheaper. If this is cheaper, take this one out and use that design. If this is cheaper, drop this one out and use the previous design. Use these to make up this. I still need to get the OR. I have those, and I got the NOT gates. I might even look for a third option, which we'll discuss later. When you see an expression written like this, AB plus, I'm just making things up, A naught B plus CD. These are known what? Products, right? And at the end, what do you do with them? Add them. That's known as sum of product. Sum of products. If the expression is written A plus B times A naught plus C times A plus C plus D naught, this is known as what? Product of sums. Product of sums. In some cases, this is give me the sum of product, or let's say give me the product of sum. So here's the book, talks about a sum of product expression. Sum of product, SOP, that's this one. Often written as SOP is one or more product terms connected by an OR operator. These are product connected by an OR operator. The other one, product of sum, one or more what? OR gates connected by an AND gate or a multiplier. A standard product of sum is called, by the way, a minterm, that's called the max term, is a product term. So standard product term is also a minterm. This is known as the minterm. Sum of product, we call that the minterm, that's also the max term. You'll see that later somewhere in the course. So let me take an expression, see if I can simplify that, and see how Boolean algebra works here. The book also will ask us to count how many terms do you have. 4 product, 3 product terms, 3 product terms. Let's define here. If you look at this, can you see it on the screen? That might be easier just to put it there. This has W bar, X, Y, Z bar. That's one term, another term, another term, another term. That's known as 4 product terms. There's a product, a product, a product, a product. This one, there's a product, there's a product, x. We say, well, that's not a product. Well, you can make it a product. X times what? 1, isn't it? So that's why this is a 3-term product. 1, 2, and 3. This one, x plus y plus z, or x bar plus y plus z. I said, well, you can make this x bar times 1, or if you don't want to do x bar times 1, you can make it x times x. Z times z, y times y, x bar. That's also 3 product terms, or together. This is 1 product term. Only addition and subtraction will separate them, actually. And this is 1 product. There is no addition or subtractions. It says, what's a term? A product term is 1 or more laterals connected by an AND. 1 or more. You have 1x. 1 or more, that's 1 term. That's 1. That's 1. That's 1. That's 1. So as the problem gets bigger, when you look at this, how many product terms do you see there? 1, 2, 3, 4, 5 terms. Each one has how many inputs? 3, what's 5 times 3? 15. This one, 1, 2, 3 terms. This has 2, this has 2, that has 3. What's 2 plus 2 plus 3? 7. This one, 3 terms. 2, 2, and 2, that's 6. This one, 3 terms. 2, 2, and 2, that's 6. So you might hear on some of the homework assignment how many terms and how many laterals we're using. Each one of these has 2 laterals, and there's 3 terms here. 2 times 3, that's 6. So let's see, how do we simplify these? You're given a problem like let's look at this problem and see if I can simplify it. That's a minterm problem. X bar, y, z bar, plus x bar, y, z, plus x, y bar, z bar, plus x, y bar, z, plus x, y, z. And the question, can you simplify that? Well, I notice on the first 2, I just happened to notice, looking at them, I can factor out what? X bar y. If I do that, what's left? Z bar plus z. What is z bar plus z? That's an OR. What is 0 or 1, or 1 or 0? That's always a 1. So that's x bar y times 1, which you end up with what? X bar y. Let's look right here. Again, I can factor what? X, y bar. And what's left? Z bar plus z. What's z bar plus z? That's a 1. So that's x, y bar plus x, y, z. So we just took that expression, which is 1, 2, 3, 4, 5 AND gates, each one 3 inputs, replaced it with this circuit, 3 AND gates. And we always try to simplify more if we can. In some cases that's possible, in some cases that's not. Now the question you might have is like, where do you come up with these expressions? Where are you getting these from? And I'm sure some of you are asking that. How do you come up with these? Now, remember your 7-segment LED driver? Remember we looked at it last time? Let me just show it to you again. And show you how we come up with these expressions. This is the 7-segment LED. It looks like this. And that thing was labeled A, B, C, D, E, F, and G. So here's my I have 4 inputs. I'm going to call them, what am I going to call my inputs? A, B, C, D. So let's call the inputs what? 0, 1, 2, 3, it's 4 digits. So when you type in, I could use W, X, Y, and Z. That's even better than all this. Here we go. W, X, Y, Z. When you type in 0, 0, 0, 0, which one of these you want to be on and which one you want to be off? So this is A, B, C, D, E, F, and G. When you hit 0, isn't that equivalent to 0? So you want the outside one to be on, but not G. So you want G to be 0, and the rest of them to be what? 1. You want A, the light to be on. You want that light to be on. 0 means off. The G is off. When you type in 1, you got to decide now which edge you want the 1. Do you want this side or this side? You're the designer. B and C. So you want B on and C on, the rest of them are zeros. When you type in 2, that's the 2. 2, I probably want to have A, B, G, E, and D on. F and C, I want them off. F and C. Because I want the 2 to look, so this is the 0. That's the 0. This is the 1. The 2, I'm going to make it look like this. Is that a 2? The 3. Is that a 3? So which one's going to be off? F and E? 4, 3. The 4. The 4. Isn't that a 4?
Backwards.
Oh, yes. I have the other one. That's the 4, right? So I want A off, B, C, B is on, C is on, D is off, E is off, G is on, and F is off. 5. B and E are off. Oh. That's the 5. Yep, I'm missing 1. The 6. Now the 6, you can decide if you want to be cute with it and go like this, or you don't want to do that. It's up to you. That could be don't care.
We almost backwards again. Isn't it? Not?
6, no.
I'm crazy. I just
6B is the only one that's off.
not backwards at all.
7.
Cool. Like awesome.
That's the 7. A, B, and C are on. The 8, all of them on, right? The 9, that's the last one, which is what? The 9, or the 8, and the 9. The 9 is like this, right? No E. And what about the 10, the 11, the 12, where there's no such thing? You gotta decide what are you going to use. So in this case, I'll say I don't care. Just do these. So now I can write the expression A. I want it to be 1 when these guys are 0. Well, the only way to get a 1 when these guys are 0, if you have an AND gate with all the inputs are complemented. That'll give me that one. Also, I want to have a 1 right here. When this is 0, this is 0, this is 1, that's 0. So that's W bar. I want to complement that. I want to complement X bar, leave the Y alone, and Z bar. That's this one. The next one is this one. These guys 0, these are 1s. So an AND gate, complement W bar and X bar, and leave Y and Z alone. I don't want to complement these. That will take care of this situation when you have 0, 0, 1, 1. Will give me that 1 there. Keep going right here. 0, 1, 0, 1. W bar, X, Y bar, Z. Next, this one. W bar, X, Y, and Z bar. Next is this one. W bar, X, Y, and Z. Next is this one. You want all these to be 1. W is 1, X is 0, Y is 0, Z 0. And finally the last one, when this is 1, 0, 0, 1. So that becomes the function for the letter A. You got to build a circuit for that. And if you simplify it, well, here we go. There's 4 inputs. That's 1 chip, 2, 3, 4 chips for the OR gates only. Then you're going to AND them together. 1, 2, 3, 4, 5, 6, 7, 8. So I have a problem. I need right there 1, 2, 3, 4, 5, 6, 7 chips on the board. Just for the letter A. Because I got to OR them. 4 inputs. 1, 2, 3, 4, 5, 6, 7, 8. I got 8 input OR gates. My chip comes with 4 input OR gates. So I can take the top 4, put them in 1. I can take the bottom 4, put them in 1. That's these bottom 4. But now I need another chip to take these 2 guys and put them together, OR them together. So I'm looking at, that's 1 chip for the AND, another one for the AND, another one for the ANDs, that's 3, another chip for the ANDs, that's 4. 4 chips, 5 for this, and 1 more to OR these, that's 6 of them, without the NOT. I'm in trouble.
Can you explain the usage of the knot to get the 0 to 1?
Well, you want to get a 1 here, right? The only way to get a 1 for this case, if you take, to get a 1 out of this, you want a chip, an AND gate that will look like this. You want the A to be going through the NOT gate, B going through the NOT gate, C going through the NOT gate, and D going through the NOT gate. When these guys 0, 0, 0, 0, I'm looking at this case.
Do you mean WXYZ?
Oh yes, WXYZ, I'm sorry. WXYZ, it doesn't really matter which one's which. So when you put 0, 0, 0, 0, so this will be what? 1, 1, 1, 1. What's the result of this AND gate? 1. So this AND gate will only give you a value of 1 only time. You'll see a 1 here when you hit 0, 0, 0, 0. Any other one, this will give me a 0.
Could you use an OR gate for that and just make one of them?
No, because that will cover more than one case. Like OR gate when what one?
Yeah.
You know? So you want to make sure this only happens when all of them are zeros. So the only way, if you build it like this actually, these knots with that AND gate will guarantee me a 1 here when all the inputs are 0. Now I'm going to do the same thing for this.
Oh, it's just for A. Okay.
For the first case.
I see it.
For this one. For this case here, when I have 0, 0, 1, 0, it will look like this. W X, oh, I'm going to put the knot here. That's the X knot. Y is fine, and Z with the knot. And this will give me a value of 1 when you have 0, 0, 1, 0.
Oh, okay, I get it now. Cool.
So this will be 1, 1, 1, 1. That gives me the 1 there. So that covers that one there. So that's where this expression coming from. It's not just like we just make them up, put them in. And I got to do 1 for A, 1 for B, 1 for C, 1 for D, 1 for E, 1 for F, 1 for G.
Oh, geez, it's gonna be a big board just for
Oh yeah.
something so small.
Yep. If you decide to design that way, yep. Is there any other options? Yes. There's other device on the market that we can use. A ROM might be a good choice to use built in. To program the stuff in it, plug it in, attach the A, B, C, D, and ready to go. But right now we didn't cover that. So your design, you're going to be building small ones in the lab, not a big one, but you'll see when you build them, they're not really small. There's about 50, 60 wires going through it for a simple design. Because first you have to power that chip. Let me try another one for Boolean algebra quickly there.
Yeah, me too. I'm saying shoot.
Let's say we have this one. That's, God, my handwriting. W,
See, you can't just waste paper like that.
flip it over.
Inside joke, somebody sent him an email last semester that he was wasting toilet paper in his math videos. Someone got that.
Yep. Somebody wasn't happy with me.
What'd
Let's
you say?
see.
I forgot. What'd you say?
I crumbled some papers and throw it to, yeah, no. Let's say I want to simplify this. By the way, this is known as what?
Product of sums.
Product of sums. Now I want to simplify it. Well, let's see. Let me look at the first two. I can FOIL them out. See what that does. W and W plus W and X bar plus W and X plus X and X bar. What's W and W? W. WX bar plus what? WX. What's X and X bar? 0. This group here, I can factor out what? W 1 plus x bar plus x. 1 added to anything, it's an OR gate. If you have an OR gate with one input 1, the result is what? 1. So this is really a W. Distribute that again. That's W and W plus W and Y. So what's the result? Factor W out. What's left? 1 plus Y, which is what? So that's W and 1, which is W. So you have an option to build this when you're in the lab, to design this. If you go to the top function, that's an OR gate with W and X OR together. We have another one, W, X going through a NOT gate. We have another one, W and Y all OR together, and the result now is what? AND together. That's one way of designing that. Or you can take a wire from W, no gates, and stretch it out. That's what this one tells me. I don't need to use any of the gates, whatever W is. Gone, 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 gone. No add, no OR, no NOT gate. In this case, that's a W. Just take a wire from W and attach it to whatever you need to attach it, the rest of the circuit.
That would totally work.
Yep, it will give you the same result as this.
Is that normal, or did you just come up with this example?
I just made that up.
Alright.
There'll be a lot of them. Like you look at the previous one, Nico. What is the previous one? We simplified. This one, 1, 2, 3, 4, 5 AND gates and one big OR gate. Replacing it with 3 AND gates and a smaller OR gate. 5 AND to 3. We lost one chip already off the board.
I mean, it was really drastic.
Well, I played with this to make sure
Yeah, it makes
you get the W's there. But it's possible when you do the math, you know. Something might happen, like falls off the whole thing.